you're not interested in this, now is a good time to leave. My name is Mihai Surdean, I'm the instructor. All right, so what we're going to cover today are 4 things. I'm not sure we're going to finish today, but these are the 4 things in this lecture. First thing you should always ask yourself is, why should I take this course? I hope I'll answer that. Then we're going to go over admin issues, who's the instructor, who's the TA, etc., etc. Then we're going to get started on actual stuff. So we're going to discuss a very common information retrieval model that's very simple, but it's very widely used. For example, Gmail uses this. So we're going to cover this. This is also going to be your first homework, which has been posted. Right? And then we're going to do a course review, going over the topics we're going to cover the rest of the semester. So why you should take this course? So this is my very scientific explanation of why you should take it. Nobody goes to page 2 of Google. How many times have you done it? Yeah, 1 person, right? So not commonly, right? So it's very, very important to show good results on the first page. Why is that? There are many reasons why you should do that. Or the company, Google, should do that. Anybody? Save time, yes.
The best results aren't at the top. Why should they use your search algorithm?
Exactly. What's your name? Sorry. Ben?
Abigail.
Abigail. Right. So in general, these 2 fall in the class of usefulness, right? You want to build a tool that's useful, right? Now, what else? So we covered usefulness. Now, there are at least 2 other reasons why you want to show good stuff, relevant stuff on the first page. Michael?
People's attention are shorter.
Yeah, that's still in my, yes. And the older you get, the shorter it becomes. But yes, so that's still sort of under usefulness. You want to build a tool that provides the most useful information as quickly as possible.
If they don't get the results right away, they will come back to the site.
Right.
You'll go out of business.
Right. Yes, so all this to me falls under sort of the usefulness bag, right? But there's also the ethical issues, right? So Google has lost a lawsuit in the European Union because people have demonstrated they promote their own services, right? So you wanna, on the first page, you wanna show good results, and by good results I also mean ethical results. And we're gonna discuss ethics in AI a little bit later on in the course, right? So you wanna be honest, right, on the results you show on the first page. You can't just show Google services. The last reason is financial. Anybody knows what's the financial reason?
The ad targeting.
Ad targeting, right? So the more time you get people to spend on your first page, or whatever page, the more likely you are to click on an ad, which means the more likely you are as a company to make money, right? So there are a ton of reasons why the quality of the results on the first page becomes very important, ranging from ethical to financial, right? So to do that, you need to take this course and actually go and Google There's another reason, and this is my favorite example why information retrieval is useful. So this is a quote. I'm going to give you the link in one slide. This is one person who literally single-handedly increased the productivity of the world's scientists by 10%. One person. 10% worldwide increase in productivity. How many of us are going to claim this when we die, right? Not many. This guy did it. Do you know who this person is? Nobody knows, but I did it.
Not by name, but is it the guy who made Google Scholar?
Yeah. Sorry, what's your name again?
Adam.
Adam. Yeah, so this is the author of Google Scholar, right? And I'm old enough to know that when I started my PhD, I still had to go to the library, actually fetch the physical journal and browse it to see, is there an article that I care about, right? Now, nobody does it, right, because of this guy. And the algorithms behind Google Scholar are algorithms we're going to cover in this class. Right, so let's do some, so I hope I sold the course. Let's do some administration things next. So I'm Mihai, I'm the instructor. That's my email, I'm in 746. My office hours are Monday to Wednesday, 11 to noon. If you can't make it and you arrange a meeting with me, I'm generally very open. So just let me know a day ahead of time. And this is, Enrique is in the back of the class, he's the person taping the lecture. And he's the TA, he's done it before, he's very good. His office hours are Tuesdays and Thursdays from 11 to 12:30. There's a website. The website is essentially just an anchor point for this course. I'm not going to maintain it too much, but you can see the syllabus, you can see the office hours, and all this information. There's going to be a Piazza. There is a Piazza website that I encourage everybody to use for questions. You can ask questions whichever way you want, anonymously, not anonymously, but it's better if we have a discussion about the issues. Sometimes students have a better answer than I do, and that's great, because part of your grade that we'll discuss in a minute is going to be in-class participation, and this counts as in-class participation. So let's have a discussion about the issues on Piazza when you have a question. See the syllabus for Code of Conduct, which means let's behave as normal adults. Classroom electronics. I'm okay if you use a laptop or a tablet for class material, but if you believe that you're disturbing the people behind you, meaning their eyes are attracted to your screen instead of the board, then please move in the back so you're disturbing fewer people. DRC accommodations. If you need accommodations, special accommodations, let me know or let DRC know and we'll handle it. Non-discrimination policy, self-explanatory, but there is additional stuff to that. So for some of you, the material in this course might be easy, right? So if that's the case, let other people speak. I'll try to organize these lectures as a discussion. If you know all the answers, give other people a chance. Do not interrupt other people and so on and so on. Academic integrity, we'll talk more about that, but don't cheat. And most of the materials will be in D2L. I think all of you have access to D2L, and I'll keep it up to date. Questions so far? Okay, so I haven't said it before. Let's try to make this as interactive as possible. There will be a part of your grade which is in-class participation to force you to speak out. So be interactive. So prerequisites. So I tried to make this course as self-contained as possible, but this is a 400 level course. So if you made it into CS without programming and without understanding what the data structure is, then first you shouldn't be in CS, and second of all, you shouldn't be in this class, right? So you should know how to program a little bit. And you should have basic understanding of basic data structures, like what's a tree, what's a hash map. And ideally calculus. I will cover all the math background in this course, but it's going to be easier for you if you have some background in calculus. If you don't have any of this, let's discuss. But you will know soon enough if you can survive or not. For example, does this look scary? So in this course, we will show actual code once in a while, but most of the algorithms will be shown in this type of pseudocode. Right? I'm not asking you to understand this algorithm now, but does this look scary? Does a while loop look scary to you? Does the if then else statement look scary to you? If it does, you might have a problem. I suspect it's not an issue for most of you, but just as a warning. Similarly for math, we're going to look at this type of formulas, right? You're going to have summations, you're going to have square roots, we're going to deal with vectors, I'll explain what vectors are and so on. So if this looks awfully, scary to you, talk to me. So you're going to have to program. So in the first homework, there is one part that's programming, and you're going to have a big project. We'll talk more about the projects in a minute. But there's going to be a decent amount of stuff that you have to program. So I don't really care what program languages you use, but historically, people have used one of these four, typically for this material. Scala, which is essentially a new variant of Java, Java, Python, or C, C++. So let's take a quick look at some of these. Java, I think, is the most common one that CS students use, and I hate it. But it has pros, right? It's pretty fast. It's probably the most common language actually used for information retrieval. NLP stands for natural language processing, which is sort of the broader class of this type of problems. It has clean exception handling. If you're old enough to program in C, I'm old enough to don't want to handle core dumps anymore. Right? So Java takes care of that by giving you an exception, and you know where the problem was, and so on. It's statically typed, which is awfully important in this course and in machine learning and natural language processing in general, where you deal with fairly complicated data structures. It has garbage collection. I worked in industry, and I remember spending 3 weeks hunting a memory leak and wanting to kill myself because of that. And Java pretty much takes care of that. And there are several great ideas. Cons, the syntax is too verbose, and it has inconsistent semantics. What I mean by that is, let me actually show you some Java. Very basic Java. Okay. This is something that pisses me off to no end. So this is, everybody know Java? Raise your hand if you don't know Java. Okay, good. So this should be self-explanatory to people, right? So in Java, you can create an integer in different ways, right? You can use a primitive type, like int, or you can use an object type like integer, right? First of all, you shouldn't be allowed to do that. Why do I have 2 different data structures for the same semantic type? Right? It's an effing integer, right? I should be able to declare it in one way alone. The fact that you want to store it internally as an object or as a primitive type, that's the job of the compiler, it's not the job of the program. And things get worse, right? If you try to compare things with double equals, who wants to volunteer a guess on what the output of this program is?
So you'll have true, false, false, true.
True, false, false, true. Let's see. A equals B, true, false, false, true. So the last, okay. Anybody else? Let's get more votes. True, false, false, true. Let's write them down. Anybody else? You don't have to be right. My point is that this is messed up, right?
Yeah.
Trevor?
I think true, 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 false.
True, 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 false. Well, I'll tell you, none of it is right. Somebody else? What's your name?
So say that it's
Kumpa. Roy. Okay.
I thought false, 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 true. It's really false.
Okay, I don't want to drag this for too long, so let's just run it. You don't have to believe me. None of you are right. It's false because in Java, double equals for objects compares by reference. And since we created these objects twice, they're going to be allocated in different places in memory. Even this, it no longer holds for all the all the JVM versions, because it turns out that all the JVMs used to cache integers lower than 1024. So when you do a new integer 1, it's actually going to a pool and picking the same integer 1 object. So in all the Java versions, the first output was true. And the other ones are true because the Java is smart enough to know how to compare a primitive object with an actual object by now. This was also false in the past, right? So anyway, the point that this is messed up, right? We shouldn't, as programmers, we shouldn't have to deal with this type of things. And this extends across the board, right? It's really, really annoying. All right, so back to the lecture. So for these reasons, and the fact that it's really verbose, and we'll get to the verbosity in a minute, I hate it. And for that reason, Scala was designed. Scala was designed by one of the authors of the Java language. And it's designed to be the way Java should have been if Java hadn't promised backwards compatibility. They made some mistakes in version 1, and they had to carry them over because they promised that. It's supposed to be an enterprise language. So they couldn't change those. And Scala said, well, screw this. We're going to start from scratch and do it the right way. And they came pretty close to doing it the right way. So Scala is a language that runs on the JVM. So it has essentially the same speed as as Java. It's considered a hot language in fields dealing with data science and machine learning. In fact, the salaries, if you look on salary.com, the salaries for Scala programmers are slightly higher than Java programmers. It has the same exception handling as Java, actually better, because you don't have to declare the exceptions explicitly. The compiler generates those. You don't have to, when you declare a method, you don't have to say that it throws this type of exception. The compiler detects that and gets it for you. It has very minimalist and clean syntax. I'll give you an example in a minute. It has consistent semantics, so when you declare an integer, there's only one way to do it. And double equals always compares by value. So code equivalent to that would always be true, because it compares objects by value, not by reference. It's statically typed just like Java. It has garbage collection just like Java. It has IDs. And importantly, it's fully compatible with Java. So you're not starting from scratch. There are other really nice languages like Haskell. The problem is Haskell is its own environment. So if you want to switch to Haskell, you have to start everything from scratch. With Scala, you don't. You can use everything that Java has just like that. It's exactly the same syntax. So you just type Java code in Scala and it works. So that's kind of cool. Cons, it has what somebody called dark corners. Scala was designed by really smart people, and the language can do a lot. And when you want to do really, really fancy things, it gets kind of strange. The solution is just don't do it. I never do it and I'm happy. And backwards compatibility is not guaranteed. That's a problem if you're a big company like Google and you invest $1 billion in software. It's not going to be a problem in this class. So let me give you an example. So I need a volunteer who wants to volunteer to write some Java code. It doesn't have to be perfect. I'm not grading it. One of the students, no. Begin. Only if you want. You know Java, right?
Yeah.
Cool. All right, so let's write the tiny Java program that takes a list, or an array list, or whatever sequential data structure you have, and generates another data structure where all the elements in the first one are multiplied by 2. So if you have a list that has 1, 2, and 3, the second list should be 2, 4, and 6.
Okay. You don't have to write fully runnable Java code. We can cut some corners. While she's doing that, let's see who finishes fast. So Scala has a REPL loop, which stands for read, evaluate, print loop, which Python has, but Java doesn't. So in Java, every time you want to do something, you have to do what Abigail is doing, meaning write the whole program. Right? Whereas Scala has this. Can you guys see this one? So I want to create a list with 3 elements. And I want to multiply each element by 2. So well, let's wait for Abby to sacrifice the class. Thank you. Yeah, so we'll talk about that in a minute. So thank you. First volunteer. So the main issues here are that Java is a procedural language, meaning you have to tell it exactly what to do step by step, right? That's how it works. Whereas Scala takes hints from Haskell and Python, and it incorporates object-oriented programming with functional programming. And functional programming is essentially, in a nutshell, a code that allows you to pass functions as parameters, right? So let me explain you what this does. So here, this is just me creating a list of 3 elements. Map is a function that takes another function as an argument and applies this function, whatever this is, on each element of the original collection. The function simply takes the current element on the list. Underscore is simply the current element where map is. So it's going to recursively, well, sequentially apply to 1, 2, and 3, multiplied by 2. And map creates a collection that has the same type as the original collection. Right? So basically what this is simply applying, multiply this by 2 to each element of this list, and return a new list with the new values. Right? If you know Python, Python has a similar thing, right? Haskell, I'm sure, has the same thing. So, much more concise. It has a REPL environment, so you can test things very quickly. And just one last example, if you want to create a class in Java and you're a good enterprise programmer, you have to provide accessor methods, right? Like get this field, set this field, that's what you're taught to do. That's a waste of time, right? So think about, I want to declare a class A with 1 field. First of all, I have to have it in the declaration of the class. Then I have to have it in the constructor. Then I have to have it in the get method. Then I have to have it in the set method. Right? So each field, if you do it properly by Java standards, each field is repeated at least 4 times. Right? Whereas in Scala, if you want to declare a class, let's say A, this is it. This is how you create a class. If you want to make the field read-only, you set it as val. So this means this only has, you can only access it as a read-only field. If you want to access it as a read-write field, you declare it as var. And that's it. So this provides a constructor. This tells you how you can access the field, and you don't need to write accessor methods. And so on and so forth. So if you don't believe me, I can recommend the book, but Scala is beautiful, and I switched to Scala 3 years ago, and I never looked back. So if you want to challenge yourself in this class, we're not going to write a lot of number of lines of code. So I think this would be a good opportunity to actually challenge yourself and learn a new language. It's going to be worth it. It's going to give you better marketing things to claim on your CD, if nothing else. Python is another option. And Python does have advantages, right? It has a clean syntax, so I would argue it's not cleaner than Scala. It's popular, right? There are many libraries that exist. It has exception handling, and has easy access to GPUs, because it's easier to interface with C, and C has been implemented on GPUs. It's slow. I'll give you a screenshot in a minute to demonstrate this. And it's dynamically typed. Both these things are killers in our field, because suppose that you write something that takes 1 day in Java. In Python, it's going to take 20 days, right? So from getting results overnight, you get results next month. That's a big difference. And it's dynamically typed, and as I said before, we're going to deal with fairly complicated data structures, right? And when you don't know what a data structure is, and you're working with somebody else's code, it's going to be a killer. C is fast, but you don't want to deal with core dumps if you're old enough. So here's a screenshot I got from some benchmarking website. This is the link in case you care. So you can't really see that, unfortunately, but I'll explain what this is. So this is G++, this is C, the C compiler. So basically they're as fast as they get. And Java and Scala are going to be these two guys. This is Java, this is Scala. So Scala is slightly lower because all that functional programming overhead translates into procedural overhead when you compile it on the JVM. But it's not by much, right? Python is this. So again, when you want to get the results overnight versus 20 days, it makes a big difference. Python is about 20 times slower than Java and stuff. Okay, enough about programming. So this is a textbook. The textbook is available online. So you don't need to buy anything. This is the link. It's in the syllabus as well. Grading, everybody cares about that. So there's going to be 4 assignments. It's really not that hard of a class. 2 exams, midterm and final. 1 big project that you should reserve time for. We'll discuss it in a minute. And in-class participation. So I highly, highly encourage you to speak up. Feel free to interrupt me. Don't interrupt your colleagues, but feel free to interrupt me. Right? If you have something to say or something to question. And be active on Piazza. The first assignment has been posted. The first assignment is based on the stuff that we're going to cover in a few minutes. Well, let's take a look at it now. Okay, we're going to discuss grading in a minute, but basically you're going to build an information extraction system both algorithmically and in code. So in this one, you're going to have to show me what the results are. You basically have to trace the algorithm we're going to cover in a few minutes, right? So you have to build some intermediate data structures on paper and show me what the results are for some queries, right? For those 4 documents. Then you have to extend some of the algorithms we cover in the class by yourself. And we're going to talk about optimization of queries. So you have to tell me in which way we optimize the query for execution. All this is going to be covered in the first lecture. This is a trickier question. So this one is the one that people have most trouble with. So we'll revisit this in a minute. And this is the coding part. Right? So you actually have to implement an information retrieval system that supports Boolean query. Right? And you have to send us the code, and you have to perform several operations on it. So you don't have to understand, we're going to revisit, you don't have to understand this material yet because we haven't covered anything really yet. We're going to come back to this. But if this looks awfully scary to you, that's why I'm showing it now. Right? You should think about if this is the right class for you. Or maybe wait until the end of lecture 1, and then if it still looks scary, then you should rethink being in this class. Anyway. So the grading scheme is going to be the same. We're going to discuss the grading scheme. This is a co-convened class, in case you didn't know. So there are both grad students and undergrad students. The grading scheme is the same, but grad students will be asked to do more. You'll be asked to do more in each homework, in each exam, and in the project. Just so you're aware. So the written assignments count for 300 points, midterm 200, final 275, in-class participation 25, and the project 200. So you can't really get an A without doing everything. And the distribution of the grades, of the letter grades, is expected. Questions so far? Okay. So let's talk about projects a little bit. So I'm going to give you 3 options. First option is to replicate some of the things that the Watson system did. Is anybody or all of you familiar with that? Adam, can you summarize it?
Oh, he's an AI that played Jeopardy and did pretty good. And he was made by IBM.
Yeah.
Yeah.
Right, so everybody knows, non-Americans know about the Jeopardy game. It's essentially a trivia game. What's the capital of France? Except it's not phrased as a question, it's phrased as a sentence. X is the capital of France, right? Something like that, right? Sorry, Adam?
Oh yeah, I just remember reading about it that Jeopardy doesn't ask questions as directly as that. They always ask, this is the capital of the country that Louis XIV was the king of.
Exactly, right. So it's formulated in that way, but it's essentially a question, like what's the capital of France, right? So we're going to talk more about the system that IBM built, but you can actually get, I had students perform about half as well as the IBM system in 2 weeks.
because it turns out that the big part of the IBM system is done using information retrieval technology. We'll discuss more when we get there. But you can do a lot with what we're covering in this class. And if you do that, you should be proud of yourself because you're getting half the performance of a team of about 40 world-class researchers did in 7 years. Right? And you're going to be able to do that in 2 weeks with what you learned. This is sort of a similar take on the same problem. This is a Kaggle. Are you guys familiar with the Kaggle website? Kaggle is a website that organizes data science challenges. It's really fun. I would argue that if you're into data science and machine learning, the best place to learn is not a textbook, but pick a challenge from this website and do it. Right? And this is a challenge that was posted by Paul Allen is one of the co-founders of Microsoft, and he's very interested in AI. So he founded this thing where they posted a bunch of questions that are science exam questions, and they have multiple choice answers, and your system has to pick the correct answer. And it turns out that in some cases, machines perform about the same as humans. So let's see how far you guys can get. Right, students, when we did this before in a seminar, students had a lot of fun. One of the students who graduated told me that this is the most fun thing he did as a CS student. So I think it's fun. The final option, option 3, is the fake news challenge, which isn't officially up yet. It will be up in a few days. So this is organized by a couple of really good machine learning researchers. And they get data that, meaning news articles, that were previously classified as fake news. And your job will be to build a machine that classifies them, that learns how to classify fake news versus real news. This is very close to my heart because I grew up in a communist country, and brainwashing, basically all the news were fake. So brainwashing was part of the policy, right? And we see it becoming a phenomenon worldwide, so we should be prepared for that. So I think this is going to expose you to what it entails and what the machine has to learn to do that. So I think this should also be a lot of fun. Questions so far? It sounds daunting, but so I have no idea how well we can do on this class. This is really new, right? This has just been announced, right? On the other two, I can tell you that a good student gets about 50% of these questions correctly. And depending on the data set, 40 to 60% of these questions. Right, so you can do a lot as a student. We'll have to see how well we do in this class. Okay, late work. Late work is not accepted unless something bad happened or important. And attendance is required. I'm old school enough to believe that in-person interactions work better. So be here. We are taking this lecture because we had enough students with motivated absences, which tends to happen on the first lecture, but it's not going to happen again. So in order to get the discussion that happens in the class, you have to be here. Okay, so these are the due dates. So the first homework is due in about 3 weeks. Second homework is due 3 weeks after. Midterm is on March 1st. And then homework 3 is due afterwards, and then we have spring recess, homework 4, project. So really, this is not a hard class, honestly. So it's not going to be a lot of work, but I hope you guys will have fun. You are not allowed to discuss individual solutions with anybody. You're not allowed to cheat. You're not allowed to copy. You're not allowed to steal from the internet or the usual stuff. If I catch you, or the TA, or any of us catch you doing that, you will receive a penalty larger than the value of the work in question. It may be up to failing the course. And whatever penalty I decide to do, I will file this with the Dean of Students. It's my obligation as faculty to do that. So it's not going to end up well. So don't do it. I know you can do well in this class without cheating, so don't even try. All right, questions on the admin stuff? Okay, introduction. So, first, let's define what we do. Right, so information retrieval is about finding stuff. Right, we're searching. Right, this is the core technology behind search engines. And what we're finding is usually documents. Although, as we will discuss throughout the class, the algorithms covered here are not limited to text. In fact, Pandora uses a very similar algorithm to finding relevant music. We'll discuss the similarities and differences as we move along, but it's typically documents. It's typically unstructured data, right? So this is not a database class. We're not going to do SQL, we're not going to do all that stuff. There are other courses for that. This is about unstructured information, which is just free text, which satisfies an information need, meaning you know what you're searching. You have a query that you're trying to answer.
Are we going to get into queries that you don't necessarily know what you're trying to answer at all?
Yes, there will be a lecture on that.
Okay.
But that's a whole field of machine learning and natural language processing, discovering what Ramsell called the unknown unknowns, right? When you don't know what you're looking for. So that's a whole big area of machine learning, which we're just touching a little bit. Okay. But we will touch it. And we are retrieving things from large collections, which means we have to do things efficiently. We can't be sloppy. So there's a big focus on efficiency on the algorithms we're going to cover. All right, so this is the whole thing. Right? So it's a fairly loaded definition, right? But this is essentially what search engines are doing. All right, so let me give you another motivation for why this is important. So in 1996, this is how the state of the data and the money looked like, right? So most of the data was unstructured, right? This is text, and these are databases. But the money was flipped, right? There was no money in unstructured data, and lots of money in databases. Now, 10 years after, essentially when this textbook was published, the data looked like this, right? So there was slightly more unstructured data, but a lot more money in unstructured data. Why do you think that is? What changed from 10 years? No money, lots of money. Then?
Widespread adoption of the internet by people.
No.
No.
So that's part of it, but that wasn't the cause. So Google, what's your name? Sorry. Ben. That's good. Sorry. So Google happened, but Google was actually losing money in the first few years. Hand over fist. They were losing money bad. They actually had to talk to many, many investors before somebody believed that this is a business. So Google happened, but that wasn't the cause of them making money. Something happened to Google afterwards that made them make money. What was that? Abigail?
So maybe they have to find a way to prove that they can pull useful information out of the unstructured data that's reliable?
Well, according to their paper, which they published in '98, I think, they already proved that, right? So they had an algorithm that was, of course, got a lot better, but according to the claim, they already knew how to do that. So when the company was funded, they knew how to find information. John?
Was it an increase in processing power and memory availability that allowed them to do that?
Well, that costs money. It doesn't make money.
Ads were probably.
Ads. What's your name? Ian. Ads. Right. That's what made Google a business. Ads. Right. Now, when you talk about ads, we go back to the discussion we had at the beginning of the lecture, right? You have to show good stuff on your page so people stay on the page, right? And then secondly, you have to display ads that are relevant, which is another information retrieval problem. So once it became a business, the importance of information retrieval increased significantly for these two reasons, right? And it stayed like that. Now ads are dominant, and that's why Google can do all these crazy things that they're doing, because they're making money, free, basically. Right, so IR is used in a lot of places. It's used by search engines for search, email, ads, Facebook to search your friends, posts to choose what to display on your wall based on the things that you visited, Twitter to search the tweets, HP, Autonomy has enterprise search, which is basically sort of, think about it as local Google. You have documents that you don't want to share with the world as a company. You build your own search engine locally that's not shared outside the company. That's essentially what it is. And Pandora and Spotify and all the other guys are using essentially the same algorithms for music search. So what I hope to convince you in this course is that IR is important. In fact, after offering this class in CS, the number of interviews at Microsoft increased a lot. Simply because people could claim that, well, we looked at algorithms behind WhatsApp. That's hot, right? But the last take why this is useful is that I really believe this is a gateway course to data science and machine learning. In fact, I really believe that if you haven't done any machine learning before, this is a better class to start because it's not abstract. This is always going to be anchored on a real algorithm and real data. Whereas if you start with machine learning, it could be sort of dry and abstract, right? This is applied, so it's much easier to understand and so on. So I hope that I had students who changed their careers after taking similar courses, right? So I hope some of you will do that. And we're going to cover lots of things. We're going to cover data structures, we're going to cover probability theory, programming, and of course, information retrieval. All right, so now we're actually beginning to learn new things. So we're going to talk about Boolean retrieval, which is definitely the simplest model there is. And queries are Boolean expressions, right? So we're going to use Shakespeare as an example here. So if you look at Shakespeare, queries over Shakespeare's plays, you can have Caesar and Brutus, which means I want to retrieve the plays that have both words, right? Any other Boolean operators are accepted, like Caesar or Brutus means I want to retrieve plays that have at least one of the two words. Do you think Google uses the Boolean model? What's your name? Young?
Yeah.
So why is that? Why do you think that's the case?
Oh, I didn't say that.
What did you say?
I said nothing.
I said yes.
Oh.
I'm James.
James. So why do you think that's true?
Because you have conditionals in the search, in the query. So it's yes or yes or this, and sometimes it doesn't find something that omits it. So you can force it to.
You can force it to, and funnily enough, even if you don't force it to, if you type a query, let's say your query has n words, word 1, word 2. By default today, the operator in between is and. In the beginning it wasn't, now it is. We'll discuss more about that, but now the default operator is and. So by default, it's a Boolean query. Let's skip this paragraph for a second, but basically what they do, they run a Boolean query, they get a bunch of documents back, and then they rank the documents, right? This is the biggest limitation of Boolean retrieval. Boolean retrieval doesn't perform ranking. It just tells you this document contains the two terms, right, if it's an AND query. Google has an additional algorithm which we'll cover later in future lectures to rank the documents. So Google is using Boolean retrieval in addition of other ranking algorithms. And they also do fancier stuff, so they not only search the text, but they search the anchor text. Anybody knows what the anchor text is?
That would you submit your website, if you wanted to, like GoDaddy.com, you get a page in it or a section at the top.
No, that's some, I don't know what they call it, meta description or something like that. But anybody programs in HTML, well, programs is a big word. Anybody writes HTML? What's your name?
You have images of the description of the image.
Yeah, so it's the description of the image or the description of the link, of the URL. When you do an href block, it has some text in there, right? That's the anchor text. So what Google found early on, and we'll discuss this later on in the course, is that the anchor text is in many cases more relevant to search than the actual text of the document. Right? So think about, I write a machine learning blog where I claim that I'm the biggest machine learning researcher in the world, right? That's false. But when other people link to my blog, they say, well, this is a stupid blog that Mihai has, right? So that's probably closer to reality than my actual content, right? So in many cases, the anchor text is less biased than the text in the link. You know, going back to the fake news challenge, this becomes important, right? So they have fancier ways of searching the anchor text. It's not Boolean. They have fancier ways of handling morphology, spelling correction. We're going to cover some of those, and so on. But at the core, Google is Boolean search plus ranking. Now, do you know an example in a Google product that's only Boolean search and nothing else? You probably use it every day, I do. John?
Your Gmail inbox searches?
Gmail has just Boolean search. In fact, I recently switched to a different email client because of this, right? So Gmail default search is just Boolean search, and they list the results chronologically, regardless of the match. And I'm sure you ran into cases where you couldn't find the email that you were searching for because of this. And there are startups that came up with better searches on top of Gmail. And one of them is called Spark, and it's really cool. So nevertheless, Boolean search is used a lot. And we'll discuss in a few minutes why. But first, let's see what it is. So this is the data we're going to use. We're going to use Shakespeare as data. And we want to find a place, as a use case, let's say we want to run this query. We want to find a place that have Bruce and Caesar, but not Calpurnia. I think the last one is a family name from one of the Roman families. So you could grep, right? You can say, well, screw your class, I'm going to use grep and get it done in a few seconds, right? So why is that not a solution? There are many reasons.
That only gives you lines that have Brutus and Caesar with Doc Calpurnia, not just Doc.
Right. It only gives you the line. What else? Then?
Grep is trying to scan all the documents every single time.
Grep is slow. If you run grep on a bigger document, immediately see how slow it is. Right. What else? At least another reason.
I mean, like you were just saying, that's not going to do any ranking. That's just
it's not going to
return
well,
everything
Boolean
that it finds.
Retrieval is not going to do any ranking for us.
Yeah.
We're going to discuss ranking later. Abigail?
It's also going to give you every line that contains those.
Yeah, so you have to manage that, exactly. Right. Another reason, the last reason is implementing not is kind of tricky. Right? You can do it. That's kind of tricky. So it's slow, it's line-oriented, so as it was pointed out, that's complicated. You have to manage additional data structures that you don't really care about, right? Because I don't really care which line it matches, I just want to get the document back. Not is kind of hard. Proximity operations, which we'll cover in the next lecture, are actually hard to implement with the graph. You have to put a wrapper on top of graph and find the line, tokenize the line, find the distance between the words, and so on and so forth. So here's what we're going to do. This is the fundamental data structure, which we're going to optimize in a few slides. But we're going to build what's called the term document incidence matrix, where you have the terms, each row is a different term. Each column is a different play. And for now, we're going to have a Boolean entry in each cell. 1 means that this term appears in this play. 0 means it doesn't. Right? As simple as that. Right? So Calpurnia occurs in Julius Caesar, right? So that's a 1. It doesn't occur in the Tempest, so that's a 0. Right? Simple as that. Okay, so to do this, what we do is we take the vectors. By that I mean the rows. So for now, let's assume vectors are rows. Right? So the vector for Bruce is the second row in the matrix. We take the vectors, we complement the vector of Calpurnia. By that I mean we flip the 1s to 0s and the 0s to 1. Why do we do that? Adam?
Because we want not.
Yeah, we want the not, right? So if you flip the 1s to 0, that means that this means that not is true here. It doesn't appear here. And then we do a bitwise AND on the 3 vectors. So if you do a bitwise AND, this means that the result, a cell is 1 if all the elements in the corresponding position are 1. Right? That's our result. Right? So we get a 1 here because this is 1, this is 1, and this is 1. And we get a 1 there for the same reason. Everything else is 0. Right? So this means if we do this, these are the plays that have our result. So Anthony and Cleopatra match because they have Brutus Caesar and they do not have Calpurnia, and so on. Right? Very simple stuff. So these are the plays that match. Right? Now, you can probably see where I'm going with this slide. The bigger you go, the bigger your matrix is. Right? So here's an example. If you have 1 million documents, which is 10 to the 6, each with about 1,000 tokens on average, we have 10 to the 9th tokens. Right? That means instances of words. Right? So on average, this collection will be 6 gigabytes. Now, these are each word that appears in the collection. If you unique them, let's say you end up with 500,000. Right? A lot fewer, but still. So if you multiply that, I'm giving you the answer here by mistake, but if you multiply the number of rows, which is number of unique words, with the number of documents, number of plays, you end up with 500 billion zeros and ones. That's a lot of stuff. Right? It's not going to fit on your laptop even today. Right? So this is because the matrix is extremely sparse. The solution is I gave it to you, you store only the ones. Right? So we take away the zeros, and we store only the ones. Now what's the problem if we do that? Let's look at this. If you take away the zeros, and you just store the ones, what do you think the problem is? Sorry, that? You'll be out of, so that's a good one. That's the first thing. You'll be out of line because the lines will have different lengths. Right? So this line has 4 ones. This line has only 1 line, only 1 1. So how do you store it? Right? You store it as a linked list. You store it as an array. How do you control for not going out of bounds and so on? So it complicates your life. But so that's a big problem. What's another big problem?
So sometimes you're interested in the zeros, right? If you're looking for not Calpurnian.
Well, let's trust me for a minute that we're not. I haven't proved that yet. But let's assume that we're not for now.
You have to figure out which ones correspond to which.
Exactly. What's your name?
Indra.
Indra. Exactly, right? So if you store away, if you throw away the zeros, your rows get squished, right? So the one which used to be pointing at a tempest now gets in this column, which is Julius Caesar. So how do you keep track of which is which? Right? So the data structure changes a little bit in the sense that instead of storing ones, we are now storing the document IDs. So what we're doing, let's go back to the matrix. What we're doing before we squish away the zeros, we assign a unique document ID to each of the columns. Right? So suppose you have, whatever, 6 plays here, you're going to have IDs from 1 to 6. It doesn't matter what they are, right? Just some unique ID. Right? Typically, as we'll see later on in the class, they're integers because we can do fancier compression with integers, but it doesn't really have to be integers, just some unique ID. Right? And then when we throw away the zeros, we store the document IDs in each cell. Right? So what this means is that Calpurnia occurs in play 2, in play 31, in play 54, and so on. Now what's the problem? So we took away Indra's problem, right? Not knowing from which document the entry comes from. But now we run into another problem. Remember that to do AND, we did a bitwise operation on the vectors. Can we do this now? Obviously not, right? We're no longer dealing with Boolean vectors, so we can't really do that. So this is going to be the fundamental algorithm in this lecture. But before we get there, let's go over terminology. So this is called an inverted index. And this is the fundamental data structure that all information retrieval systems use. Google has one of these. It's obviously distributed across different nodes because it doesn't fit on a single machine. But they all look exactly the same. As the course advances, we're going to add more and more stuff to this data structure. But it's always this. It's always a dictionary, which is basically the list of unique words in your collection. And postings, which is the list of documents where this corresponding term occurs. So far, so good. Everybody with me? Questions? Okay, now, before I show you the algorithm, so anyway, this is an example, right? So here's how you construct it. Let's say each of these rectangles is a different plane, right? Of course, we're simplifying here, so it's a small number of words, but as soon as each rectangle is a different plane. We're tokenizing it, which basically means breaking down the string that corresponds to all the text in the play into individual words. In the next lecture, we're going to discuss how we do that. Optional, you can do some linguistic processing like normalizing the case, normalizing the words so all the plurals become singular and so on. This is this stuff. And then we construct the index. Right, so to do that, here's how it looks like. So here's where we tokenize the text, right? So tokenize and normalize the text. So all the text becomes lowercase and it's broken down into words. We remove some of the words that we don't really care about, like semicolon. We don't really care about that. And then we list them in the order in which they appear in the original place. Right? So this is the original text. I didn't act Julius Caesar, I was killed, blah, blah, right? This is the original text. We haven't done much fancy things yet. We just tokenized it. Then we sort it. Remember that at this stage, we still have duplicates. Right? These are all the words we've seen in the collection. Now we sort them. And once they're sorted, it's very easy to build the postings. Right? Because here you know that killed, where are we? I think there might be, no. Here when we get to killed, let's say we're here, right? We know that killed occurs in document 1, right? So we can actually traverse this just once and construct the dictionary and postings. Right? So let's look at a more interesting example. Let's look at Caesar. Right? So let's say we're looking at this one. Right? Whenever we hit Caesar, the first Caesar, it's a new word. We add it to the dictionary, and we've seen it in document 1. So we add document 1 to the postings. Now when we do this, we need to keep track of 2 pointers. We need to keep track of the pointer which is the last entry in the dictionary so we can grow it. And the last entry in the postings, so we can grow the postings. Right? Now we see the next Caesar, which is also in document 1. Now by keeping track of the last position in the dictionary, we know that we've seen Caesar again. Right? You can check this in constant time. And by looking at the last position in the posting, we know that we've seen document 1 before, so we do not add it. Everybody with me so far? Then we see the next Caesar, which appears in document 2. Again, we look at the last entry in the dictionary, so we know that we've seen Caesar again. Then we go to the last position in the posting, and we see document 1. And because these guys are sorted, we can just append at the end and guarantee that the postings will be sorted. Right? So this algorithm is essentially linear in the size of this list. And it guarantees you minus the sorting, right? So let's assume the sorting is done for us. And it has two nice properties at the end. The first one is that the dictionary will be sorted. And the second one, which is actually more important for us, is that the postings will be sorted. So overall, what do you guys think is the complexity of this algorithm? Anybody okay with the term complexity, runtime complexity?
It would be O of N and N.
And what's like that?
It would be
Speak up.
O of N, but they're just going over the list twice. Oh, we are sorting it.
We
so
are
it would be
sorting.
N log N length.
Right, so the complexity is n log n for the sort, where n is the number of elements in this list. So n log n for the sort, everybody knows why. Give me a sorting algorithm. What's the one that comes to mind when you think about n log n? Quicksort. Most people said quicksort. Do you know who invented quicksort? Or why was it invented?
Normal stability.
For this thing. Quicksort was invented by natural language processing people to sort dictionaries. So I know I had a discussion when I moved here about, is natural language processing computer science or linguistics? And this is my favorite example of, do you know quicksort? That's done by natural language processing people. So anyway, n log n, right? Then this is n, right, as we discussed. You can do this in constant time by keeping only two pointers, a pointer to the end of the dictionary and a pointer to the end of the current posting. Right? And then you just traverse the list once, and all the other operations are in constant time. So now what we have is a list of sorted terms, which we're not going to use today, but it's going to be important later on. And for each word, we have a list of sorted postings. So we end up with something like this. Now, how would you implement AND efficiently over this data structure? Volunteers? It's fairly intuitive. Again, we agree we can do a bitwise operation, right? Because we're not dealing with bits anymore, right? We have integers. Somebody else who's not Ben? Michael?
It just looks like a hash table.
Well, this part is a hash table. Right? But now we want to get, say I want to implement the query Caesar and Calpurnia. I can access this in constant time because I'm dealing with a hash. But then I want to produce a list of documents which match the query Caesar and Calpurnia. How would you get the list of documents from these two postings? So we know we can get these two postings in constant time, right? Because that's a hash map. How do you get the list of resulting documents as cheaply as possible? Somebody who's not John?
You just traverse through the postings of the first one and then go through checking to see if it exists in the second one.
What's your name?
Morgan.
Morgan. Okay, so that's the first approach that I would implement. I agree with you, right? Now if you traverse, let's say we're dealing with Caesar and Calpurnia. If you traverse Caesar, the elements in Caesar, and for each element in Caesar, you can check if it exists here. What's the runtime complexity of this operation? Let's say n squared, right? Because let's say the average posting length is n. You're traversing this, and for each point in this, you're traversing this again. So it's n times n. That works. Can we do better? What's your name first?
Michael.
Michael.
So you use 2 pointers and just kind of move along.
All right. Do you want to come here and show us the pointers, how they move, or should I do it for you?
You do it.
Wrong question. Well, okay. Right. So we keep 2 pointers. Right. We start with the pointers here. We check these 2 elements. They're different. Then what do we do? This is the key operation. When 2 elements are different, what do we do?
Move up the one.
Michael, you started it, so now finish it.
Move the one that's less.
Move the one that's less, right? That's the fundamental operation. They're different. We move the one that's less. Now they're equal. Now what do we do? So we got a match, right, Morgan? So we store the match and then we move both. And then we keep going. Now you implemented the Boolean retrieval system. Ben?
The stored match though, how are we not, so we've stored that in a list, are we going to remove it at some point?
Well, that's the result, right? So you want to produce all the documents that contain Caesar and Calpurnia. So we store it in a new list. Everybody okay with this intuition? We're going to look at a formal algorithm in a second. Would you? Okay. So we're going to look at, later in the course, we're going to discuss this algorithm, but later in the course, we're going to look at how to construct this for large collections. What do you do when it doesn't fit on your hard disk or RAM? How do you split it so you keep things consistent? Right? How much space do you need for dictionaries and index? For example, based on your intuition, would you say that the vocabulary that Google has to handle is finite or infinite?
Infinite.
What's your name? Sorry.
James.
James, I'm going to do that. It's infinite, and there's actually a law in linguistics which demonstrates that. So it's not intuitive, right? If you think about it, how many words? It turns out that you can actually speak, on day-to-day stuff, you can speak a language if you know 500 words. Sounds not a lot, right? But when you're dealing with a search engine, you're indexing everything, right? There are 20,000 proteins in the human body that you have to index, right? Each one becomes a token, and so on and so forth, right? So it keeps growing forever, right? So we have to do it efficiently. How do you compress things? How do you rank things? All this is cool stuff that we'll do soon. Now, this is the algorithm that Michael just defined for us, right? So this is constant time because we're dealing with a hash. Is everybody okay with the hash map? Retrieving its posting links, again, it's constant time. Same thing for Calpurnia. Then we intersect, right? This is the algorithm we discussed a few minutes ago. So here's how it looks like, right? You start with the 2. They're not equal. Then you look for the one that's smaller, and you move that. Now they are equal, so we got a match. That's good. We store the match, and we move both pointers. 4 is smaller, we move to 11. 11 is smaller, we move to 31. We got another match, and so on and so forth. What's the runtime complexity of this thing? So remember the Morgan solution, I'm not putting you on the spot, I would have implemented the same thing, was n squared. What's the runtime complexity of this thing? Right?
It's just n, this is 10.
Right, it's 2n, right? 2 is a constant, so we can throw it away if you remember your runtime complexity theory, so it's n, right? So we moved from n squared to n. When you Google, and this could be in the millions, that's a big difference, right? From 10 to the 12 to 10 to the 6. It's a huge improvement with a very, very simple algorithm. So this is actually part of your homework. We're going to go over the homework. So it's linear. This only works if the postings are sorted, right? So this is going to come up again when we're building the indices. You want to be careful to keep the posting list sorted all the time, right? So whatever algorithm you use to build the index, it has to be sorted. Ben?
And this requires a stable sort, right? You're assuming that to get this order correct rather than
Yeah, so that's a good point. We're going to discuss later in the course how do you do incremental indexing efficiently, right? So if you're not careful, let's say you come up with a new, Google discovers and crawls a new document. Are they going to build their whole index again? You don't want to do that, right? So you have to be careful to be stable with the stuff that you had before when we add new things. So we're going to discuss that later on. Am I answering your question?
Well, I mean, it's, to get the correct out, you said you can just go through and add it to the list and the order will be correct, but that's assuming that you have a stable sort where...
Yes, correct.
That's what I meant, right?
Correct,
okay.
yes.
Can I ask you a quick question about
Yes.
the diagram here? I noticed that you have the one-line arrows and the two-line arrows. Is there like a derive versus derives or something like that?
No, this is just cosmetics.
Artistic.
Yeah, this just tells you this is the result.
Okay,
So don't worry. Anything else? Okay, so by now you should know, we're going to look at the algorithm in a minute. You should know how to build an index if you build it all at once, right? You build as a single chunk. And how to do end queries. So let's look at the algorithm before we close it there. So this is the pseudocode we're going to use throughout the class. So let's go through it line by line. This is the name of the procedure, intersect. We're getting the pointers to the two postings. P1 is the pointer which points to the beginning of the first posting. P2 points to the beginning of the second posting. Answer is the empty list. This is what this means. Right? As long as the two pointers are not nil, what we do is, if we found two doc IDs at the same position, so doc ID at P1 means the doc ID at position P1, wherever P1 is in the list. If the two IDs are the same, we add it to the answer. Then we move on to the next one. This is a singly linked list, if you remember your basic data structures. Right? We just move on to the next point. If they're not, and the ID in the first posting is smaller than the ID in the second posting, we advance P1. Otherwise, we advance P2. Right? Then we covered all the cases: equality, less than, greater than. That's it. Right? And this is what your Gmail is doing. That's all. All right, so let's stop here. Questions? All right, see you. Oh,
well, I was just going to say, what is it about the Gmail search that you don't like? Because the Boolean, to me, you would have everything in a list. You would get everything retrieved, and you could always sort by date or something else that would be important to you. Like, and would it not?
It's not really resolved. It's not really run. And sometimes you want to discuss more this later on in the course. If I search for the word wolves, and I have an email that says wolves 100 times, I want that to be right. I want to go to other